Thank you, Shai. Next speaker is Professor Tishby from the Hebrew University. He'll talk about recent advances in the information theory of deep neural networks for the computational benefits of the hidden layers and the computational benefits. Thank you, Tom.
Thank you, Amir. Actually, I have a much simpler title. So after hearing Shai, I think we are very much in need of a different type of theory. I mean, deep learning is obviously way too good in practice than some of the theoreticians are trying to convince us. So the question is not really why deep learning doesn't work, or when it doesn't work, why does it sometimes work so well? And I'm trying to give a completely different perspective of deep learning, which we introduced already something like 5 years ago, which is actually based on ideas that I've been playing with for many years from information theory, which is really focusing on the large scale of the problem. So obviously deep learning is not working for worst case, fractal-like distributions or things like this in some cases, and definitely this is not where the benefit of deep learning is. So the theory that we've been working on together with a number of people is that essentially, if we look at what happens in the neural network layer by layer, so really unlike what Shai just told you, the layers actually play a very important role in the success of the story. And we think about this layer structure as a cascade of representation transformations which essentially change the nature of the input layer by layer successively from very complex topology where things which are nearby, let's say in the Euclidean topology, are absolutely different when you move through the layers. And eventually in the last layer, the two classes that you want to separate, let's say, is it me in the picture or not, are really in completely separate subspaces of the space, and I can easily separate them with a linear threshold function or with a threshold gate. And when you think about it, I denote by X the input and by Y the label. Each one of the hidden layers form some sort of a Markov chain, which really lose information from layer to layer in a way which really refine, in some sense, the essence of the problem. So I think about it as I really look at what I call the information flow through the network, how much information about the input actually goes through the layers layer by layer, and how much it actually refined or gets rid of the irrelevant information and eventually give me only what I need with this information about the label. And this is a very old idea. It's coming from the notion of minimal sufficient statistics. And you can think about it actually as if the layers are some sort of a cascade of filters. Each layer is leaking out some of the information about the input and making the representation finer and finer. Now, I've been playing with this idea, and I've been trying to sell this idea for some years. I mean, nobody, of course, noticed it until we actually showed some simulations. Why is it important? And I just want you all to make sure that you all know what this function that I call mutual information is. Essentially, mutual information is the average of the log conditional to non-conditional distribution. Essentially, it's telling me how much information is shared by two random variables in bits. But you can really think about it as a measure of how much flows through the network. And what is really important about mutual information is that if you go through a Markov chain, you cannot gain information, you only lose information. This is something which is known as the data processing inequality, and it's a fundamental property which is really important here. I mean, I can generate a lot of noise between the layers, but I cannot gain information about the input. So we look at this cascade of information through the layers, and actually really interested, for many years I was interested to look at a real neural network and see really in these two parameters only, information about the input, information about the desired label, how does the training of the network look like? And my conjecture was that in this two-dimensional representation, which I call the information plan, this is like taking an X-ray of the system. It's actually going to reveal the structure of the layers in an interesting way. And of course, until we did some simulations, we didn't believe it ourselves. And this is a simulation done by Ravid Schwartz-Zivet 3 or 4 years ago. And essentially what you see there in different colors are different layers of a small neural network where we can actually measure the information. And this dynamics, this interesting trajectories, is actually the stochastic gradient descent training of this network. And this is actually quite striking. I mean, when we saw it first, I didn't believe that it's going to look so nice. I'm sorry, I want to show it again. So you see the last hidden layer, which is this one, is actually doing a very interesting trajectory coming up, gaining information about the input, which means improving the generalization error, and eventually all the layers seem to move to the left in this very interesting way. So if I look at these traces of the trajectories of the layers through the SGD training, this is the kind of X-ray that I get. The last layer starts in a very low information about the label, which means it doesn't predict the label at all, and then eventually rather quickly move to this point C, where there is some information about the label, but not all of it. It's not a very good generalization. All the networks, due to data processing inequality, all the previous layers do similar things. They come up. The nature of the trajectory depends on the architecture and on the number of layers and so on. But eventually, all of them do this slow motion from C to E, which I call compression or diffusion. And we see and eventually they get to the point E, where all the layers sit on some very interesting line in this plane, and they seem to stick there. I mean, the layer 5 is here, layer 4 here, layer 3 here, and so on. And on the layer eventually converge on very specific points along a very specific line in this plane, such that the last hidden layer is really doing what I want, essentially remembering only one bit about the input, which is really separating the data into two classes. Now, the really interesting question, I mean, so this is, first of all, is something like an X-ray in the sense that we didn't touch in any way the training of the network. We used TensorFlow in the plain vanilla way using stochastic gradient descent of some sort. We did actually with different problems, larger layers, real problems, CFAR, ReLUs, non-ReLUs, convolutions, not convolution, whatever you want. And if you actually look at this measure, you see similar pictures. And what I argue is really I'm trying to understand this picture, and actually I argue that understanding why this is the picture reveals a lot about the nature of SGD and deep learning, and why really the layers actually help you. Of course, they don't help you if shallow networks don't help you. I completely agree with Shai on that, but why do they actually help and how much they help? So this two-dimensional representation, really think about it as an X-ray. You don't really have to measure the information. You can take a lot of proxies to the information based on Gaussian processes, based on kernel methods, there are many, many other things. But there's something asymptotic about this story. The whole story of using mutual information becomes true and rigorous in some sense only when you talk about large problems where the pattern is very large, millions of pixels is large enough for that, and where there's some sort of invariance when you can actually talk about typical patterns and typical problems. So I argue that the whole thing is true only when you talk about typical problems in some sense. If you push me to non-typical things, and I don't know if fractals are typical or not typical, then you can get all sorts of funny things, which don't obey this. So this is an average case or typical case type of theory, which is precisely the kind of theory that computer scientists don't like. And that's why computer scientists really ignore this work to a large extent, despite the fact that it's already quite influential. Now, so the story is really to look at the relationship between the encoder of each layer, the map from the input to the layer, and the decoder of each layer, the map from the layer to the output. And what I argue is that this mutual information about the input and mutual information about the output is actually these two numbers only really give you the main part of the story. Now, I don't want to spend too much time on things that you can find on the internet in many other talks that I gave. I just want to show you that it really captures in a very nice way also the finite sample behavior. And what you see here is this, these are what I call information plan trajectories when you have a lot of data, and these are information plan trajectories when you don't have a lot of data. What is really interesting, and color here is the number of training epoch, or time of training, and you see that with less data, essentially the first phase is very similar. You very quickly fit the labels. But the compression is very different. You actually lose information about the label when you do this motion to the left. And the really interesting question is what really governs those lines. I mean, what is this line in the information plane, information about input, information about output, to which the layers converge to? Now, we have a theory which is quite old. I mean, we started in the 90s, which actually tell you exactly what is the ultimate bound. Given a problem, which means given a joint distribution of x and y, I can calculate a line, which I call the information bottleneck bound, which is essentially a rate distortion function or something like this, which means this is an information theoretic bound. Nothing can be above this line. You can only find the representations of the problem below this line. Now, here everything is very much exaggerated. In the problem that we had, the line is actually very, very close to the top, if there is some stochasticity in the room. And this line it depends only on the problem. And I actually argue that in many, many cases, the layers of deep learning actually converge to this optimal line. Not only that, the analytic structure of this line, which again is a proper property of the problem only, not of the architecture, is going to determine where the layers are going to be at the end. And indeed, in the problem I just showed you, we actually see that the theoretical line that is calculated just from distribution is this blue line, and the layers are those red crosses with the statistics of the red crosses, and you see that they converge quite convincingly to this line. Okay, so this is an old story by now. We know, by the way, for those who doubt it, that if you don't compress the representation, of course, you can keep a lot of information about the input that you don't need to, like you do in ResNets or in RevNets or in iRevNets and in many architectures actually. But if you don't use for the decoder lower information, you are not going to generalize. That's something I say in a much more profound way today because we understand it much better. In principle, you need to compress the representation. This is essential for the decoder to be efficient. And this iteration between the encoder and the decoder, each layer is really the heart of the problem. And by the way, you can do this iteration between encoder and decoder, which we do for many years using something like Blout or Emoto algorithm, layer by layer without backpropagation, and you still converge to very good results. So backpropagation is really not the issue here. Now, we know that if you actually look at the error together with this information plane trajectory, so here you see the training error or the generalization error, it doesn't really matter. You see that the compression really starts when the generalization essentially saturates, where the error essentially saturates, which means you get already to very low or error, very flat, and the gradients of the error, which really drive the whole thing, are very noisy and very, very small. And indeed, we know, again, it's a very profound fact by now, that there is a nice transition in the gradients. I mean, they move from very clean, high signal to noise gradient to very low, very noisy, low signal to noise gradients, and this is really what's pushing the compression. And again, this was something which was under debate. I was attacked by hundreds of people, but a lot of people really see it now, and we actually understand pretty well why is this happening. I mean, what is this compression, and why the compression is related to the noise in the gradients. And either way, you can see it, even if you use very clean gradients without mini batches or anything, you still see this compression. Now, one of the interesting consequences of this story, which is, no, it's not a full theory of anything, it's just another different view of what happened in deep learning, is that we see that if we add layers to the problem, we actually decrease the number of iterations. That's a prediction of the theory, which I'm not going to get into the proof now. I'm just telling you that these two phases, clean gradients and noisy gradients, essentially in the clean gradient, I converge to something which looks like a CCA, and I'm just saying it to Amir and Gal who sit here because they were the first to introduce it to me. CCA is the thing that happens when you compress a linear network. Essentially, the first phase is a CCA, and the second phase, the noisy, is adding noise to the CCA in the irrelevant dimensions. And essentially what happens here is that during this compression, the signal-to-noise ratio of the irrelevant attributes of the problem decrease, and they decrease in a very systematic way, which allows us to make very concrete predictions. We know that the mutual information between two consecutive layers really goes down to a constant, and they go down like a power law of time, where time is the number of iterations, which with an exponent which depends on the diffusion the diffusion coefficients of the problem. So this was a theoretical prediction that I made a long time ago. We actually checked it, and one of the interesting predictions of this is that the time to converge with k layers is the time to converge with one layer, and this, by the way, implies what Shai just told us. I mean, if you don't converge with one layer, you're not going to do anything good here. If this is 0 or this is infinity, nothing's going to help you. But multiply by a factor which depends on the number of layers with an exponent which is exactly determined by the diffusion of this random walk in the error space. And this is an interesting prediction, which means that more layers get you faster to the goal. And indeed, that's exactly what we see. There's a power law. This is the number of layers, and this is the number of iterations. And you see that log number of layers versus log number of iteration give you a very nice straight line. The theory is this fit with alpha, which means half is what you predict from simple diffusion. And you see that, at least in simple problems, the time goes down with the number of layers like a power law. And this is really the interesting question. Why does it happen, or how does it happen? Of course, if you add more layers, more and more layers, eventually the time goes up because there are no irrelevant features that you can separate by those layers. And that's really, I want to come to the last part of my story, which is really the most exciting one. We know that the information plan, okay, I just want to explain these pictures. So this is, again, information about the input versus information about the output, this information plan. And what you see here, this very interesting figure, are essentially what we call phase boundaries. These are places where any gradient-based algorithm is going to diverge. Not because of the architecture of the problem, but because there is a phase transition in the sense that you move from simpler representation to more complex representation. You need to split clusters, or you need to change the topology of your space. And what is really nice about it, that this is completely predictable from the problem itself, and that's precisely, I argue, or I suggest, or I conjecture if you want, this is exactly going to determine the position of the layers, layer by layer in the problem. So what I'm saying, there is a structure, this complex phase boundary structure, which, by the way, goes all the way to the deterministic limit of the problem, which tells you where the layers are going to end up in this convergence, and exactly what each layer represents in the sense of what type of features it ignores and what it moves to the other layer. And we are now studying this particular aspect of the problem. I mean, these phase boundaries, there are many, many mathematical details which I don't have time to get into, but I really believe that this information plan view is really giving us a very different, much needed, top-down type of theory, which is more like statistical mechanics and information theory, and is very different from the classical worst-case analysis of neural network, which seemed not to work, if you're asking me. So I just want to summarize. Essentially, only 2 number per layer method. This is what I call the information plan. You don't need to estimate information exactly. You can use a lot of proxies based on Gaussian mixtures or based on Gaussian processes and give you similar things, and even in very large network. The advantage of many layers is mostly computational, and we understand why. And of course, there are many, many things, especially solvable models and those phase boundaries, which are going to tell us where the layers lie and why they lie there. I just want to make a propaganda for a special issue of entropy, which is going to be dedicated to this particular question, information theory of deep neural networks. And the deadline is the end of the year, but you can still submit papers. We already have something like 20 papers submitted to this special issue. And I think this is where you're going to see the story revealed completely. Thank you very much. Any question? Yes.
The problems that we're working on as compared to the fractal problems that we heard about before.
So how much of it depends on the problem?
Right, because you showed that the more that we lost information about space, the more we had.
The whole structure in the information plan is a property of the problem. The exact trajectories which the layers are going to follow depends, of course, on the architecture. But what I argue that when they get close to this optimal bound, the nature of the encoder and the decoder are completely dominated by the information bottleneck relationship, and that's why I have such concrete predictions on what each layer represents. So you're right. I mean, the trajectory is in the lower part of the plane as some sort of complicated interaction between the problem and the architecture. But eventually, the layers are going to get stuck somewhere, and these are critical points of the original problem that depend on the features that are really important. Different problems will look very different. It's a problem-dependent theory. It's not, in some sense, a universal story. It tells me what happens in one particular data set. All right. Thank you very much.